Good. So in our previous lecture, we have presented the perceptron, which is the basic unit when building deep neural networks or neural networks which are not deep anyway. In that perceptron, we observe that there are some parameters, some weights and biases that need to be estimated and that will define how the perceptron is going to behave. In order to estimate these parameters, we're going to run a process called backpropagation, which is actually the training process for when training neural networks, when estimating these parameters. There are also other options for training, but backpropagation is by far the most adopted nowadays. So let's start with the lecture. So I'll start sharing the slides as usual. First, my acknowledgements to Kay McGuinness from Dublin City University and Elisa Seidel from UPC. Also, you have here Elisa Seidel lecture on backpropagation. Before presenting backpropagation, I need to introduce a concept that you will see in more detail in the future, which is the concept of loss function. The loss function assesses the performance of our model by comparing its predictions, that's going to be y with the hat, to an expected value, y, which is typically coming from annotations. That will be the ground truth value. For example, imagine that predicted price y with the hat of our model and the one that we actually paid, like y, that will be the ground truth. These two values, like the predicted one and the actually paid, could be compared with the Euclidean distance, that you might heard of it as the L2 distance or the mean square error, or MSE. So if we have, for example, a linear regression, we'll be solving this equation, right? And now, if we want to compare the predictive values with the ground truth, actually there should be a hat here, sorry, we could be using the L2 loss. That what it does is, like, for each of the components of the vector y, it's going to do a subtraction at the power of 2 and then add all the values and average by n, like where n is the dimension of the vector. Okay, notice that if you plot the curve of this loss, like what is going to be the value with respect to the error, this is the kind of shape that you will get when you get an Euclidean loss. Okay, so there are many other losses when training neural networks, but for now, to move forward into the explanation, I need to introduce that. So the loss function kind of is going to guide the training process, so that when we update our parameters, our W and bias here, I will try to minimize the total error. That's going to be to minimize our loss function. In particular, let's assume a very, very, very super simple system, which is like even less than a linear regression. So actually, imagine that we want to minimize a loss function, LW, and we only have one parameter to estimate this, W, okay? And we use a L2 loss function. We may have, like, our parameter would give us, like, for a certain value, right, this loss function. So this loss value. So just imagine that we want to, I would say, train our linear regression with only one parameter, and we start with some random value, okay? We feed one of our training samples, one of our pairs X and Y's. We make a prediction, Y with a hat, okay? And this prediction, as we can compare it with the ground truth, we can compute a loss value, okay? And here, this curve, what it's telling you is that if your loss function is an L2 loss, like, depending on the value of the parameter you're trying to estimate, this is how your loss will evolve, because it's a squared law. It follows a square law, because there's this square here. It follows a quadratic form, okay? Then, when we are training deep neural networks, or neural networks in general, what we are going to do, it's to follow an iterative process. So imagine that that's it, right? We start our training process, we initialize W at this value, this is why it states W at T, at time step t, okay, and give us this value, this error of the loss. Okay, based on this graph that you see here on screen, if you are going to update W, so if you are going to update W, the weight, what would you do? Would you increase it or decrease it? You please answer on the chat. Like, if this if what we are looking is that a screenshot of the loss at time step t in an iterative process, in which we're going to be iteratively estimating W, and you are here, and we have a value that WT that gives you this loss function. What would you do now? Would you increase it or decrease it? Okay, so the answer that is on the chat is decrease, and that's correct, because notice that this W, okay, it's mapped here. This is all the range of possible values that W can take. Okay, so different values will result in different losses, and this is what we are plotting here. Okay, and based on what you are seeing, you see, hey, I see that the minimum loss is over here, so I would need to do is to decrease. I would need to go into that direction. Okay. What it's very important here that you know is that while this is very nice because I just plot you here the loss and you can all see that the minimum is here, this is not the case when we train neural networks. We don't know where the minimum is. Okay, so we don't see this very nice blue curve that I plot you here. We don't see the actual shape. But we'll need to take decisions about how to update the parameters during training. Then if you don't see the minimum, but you see something just over here in the neighborhood of WT, which operation could tell you which way to go, to the left or to the right, in this example of the operations that you know from calculus? If you can look here around. The derivative. Yeah, thank you very much. Okay, so the derivative will tell you like in which direction this function is kind of increasing or decreasing. And the direction, in this case, it's a loss. As we want to decrease the loss, if we compute the derivative, it's going to give us like some value which is going to be positive in the direction. So we want to do is to go against the direction of the derivative. Okay, and the answer is like now I can know with the slope, let's say with the derivative, I can know more or less in which direction to update my parameter for the next iteration. Like the next question is how much, right? How large should the step be? So this, what you probably already know as the gradient descent algorithm, which is basically telling you when I have my parameter WT and I want to update it at the next time step, what I'm going to do is I'm going to compute the derivative, is what you have here, of the loss function with respect to the parameter that I want to estimate, W, at the point where I am now, WT. And what I'm going to do, I'm going to go against the derivative. This is why we have a minus here. So we're going to go into the direction of the derivative. And there's still another parameter that I didn't comment, which is this alpha. This alpha is what we call the learning rate. The learning rate is what we call a hyperparameter. It means that it's a value that you will need to define, set yourself when you train your deep neural networks. And it's normally one of the challenges when you train neural networks to choose the right learning rate, and in addition, often to change it, like through the training process, through the optimization process, typically change it to try to that our parameters can find a combination that decreases the loss. So the lower the loss, the better the predictions of our model will be. Okay, and remember, our curve will not be as nice as this one. Okay, and in addition, we will not have one parameter W. We're going to have millions of parameters. Each of these W, it's each of these weights of the perceptron that I showed you earlier, the weight and the bias. And usually you're going to have thousands of neurons. So that's going to explode into millions of these double weights. And each of them, you need to update it following, if you want, this approach. There are other optimization techniques, but we are going to focus on this one, which is the most popular. Okay, so this is what we want to do. We want to apply something called the gradient descent, and here the trick or the challenge is basically, I told you that the learning rate is a hyperparameter. We set it and maybe we change it, but the challenge in general is just to find the derivative of the loss with respect to each of the parameters of our model, of all the weights in the perceptron, or when we have a network, all the weights in our network. That's going to be the big challenge, and that's what most of the computation, most of the GPUs are computing when training deep neural networks. Okay, so backpropagation, which is the topic that we are discussing, will allow us to compute the gradients of the loss function with respect to all the model's parameters, okay, which is what we want to estimate. Also, with respect to the intermediate data, normally that's not very interesting. And that's something that normally we say that the gradients will flow from the output of the model where we compute the loss backwards, because you'll see a network that it's where the gradient will be changing, updating the parameters. And actually, that's why some years ago in this conference, the NIPS conference, Intel, when they presented one of their latest chips, they actually brought Florida, which is a very famous rapper, okay? Because it's Florida because it was kind of a joke of the part was called "Let the Gradients Flow." Okay, that's where they presented a new chip for deep learning. Okay, let's try to understand how can we estimate parameters if in a neural network. We'll focus in a simple case first, which is just the perceptron. Okay, in order to estimate the backpropagation, understand how it works, we'll need to understand which are the operations that are implied when we are computing the output of a perceptron. So here you have a perceptron with a sigmoid activation, two inputs with the two parameters, a bias, and this is the range of output values. Okay, so let's see, what is the computation graph, which means like which operations are executed and in which order of a perceptron if it has a sigmoid activation. So the concept of computational graph, it's very useful to understand how the neural networks are trained and how backpropagation works. This is what the computation graph looks like. So we're going to draw a graph that shows the order of the operations. So remember, the perceptron, the first thing that you do is you compute the product of the weights with the input. This is a product, the two pairs of products. We add them, we add the bias, and here finally we compute the sigmoid activation to the input. Okay, what you see in this screen is the computational graph of a perceptron. Now we have this example. Let's imagine one simple example in which I set values to the input weights and the input data. So these are the input weights and the bias. I set some arbitrary numbers. Some arbitrary numbers to the input data, and if you follow the computational graph, what I'm drawing at each point, it's the results of all the operations. So you see here, if you follow in detail, that at the output of this computational graph, we have a result of 0.73, whatever this value means. Okay, when we go from the input values to the output of the network, we talk about the forward pass of the computation. Our challenge here, remember, is that we want to compute the gradient of the loss with respect to each of the parameters of our, in this case, of our perceptron. So here our parameters are W1, we have it here, W2, and the bias. And what we'd like to know is what is the partial derivative of the loss for each of these parameters, because it's not obvious, because W is here and the loss is here, and there are like so many intermediate steps, and this is what we need to solve. In order to solve that, we are going to apply something you already know about, which is called the chain rule, which is the derivative of nested functions. So in this example, you have a nested function, or 1, 2, 3, 4 nested functions, which kind of says like if I have an input data x1, I have 1, 2, 3, and 4 nested functions. This computational graph, which is kind of very simple,
you have it decomposed here below with classic notation. I'm just defining the names of the intermediate variables at the forward pass. Okay, now, what does the chain rule tell us? So the chain rule tells us is that if we want to find the partial derivative of the output with respect to the input, what we need to do, so this is what we want to find. So so the question is like, how does a variation, a difference on the input affect the prediction? How does a variation of x1 affect the output y with a hat? So the chain rule tells us that what we need to do is to compute the partial derivative and do the product out of them. Let's try to analyze in a bit more detail how to compute this. What does it mean? So let's take it from step by step. Let's look first at the very end. So let's consider that we call this delta 5 to the partial derivative of y with a hat with x5, which is exactly the same. So in this case, the partial derivative is just 1. So which on other words, it means that a variation in x5 directly affects on y with a hat with a 1-to-1 factor. Let's take one step backwards. Now things become more interesting here, right? So the question now is, if we want to compute delta 4, we want to know, like, how does the variation on x4 affect the predicted y with a hat? And now it's when we apply the chain rule, because it's telling us that this is the variation of y with a hat with respect to x5 multiplied by the variation of x with a x5 with respect to x4. This first term is what we call delta 5, and this new term, that's what we can like reformulate that. So the variation of x5 with respect to x4 to x4, that is the partial derivative, or the derivative of g4 evaluated on x4. This is what it's telling us. It's telling us just compute the derivative of g4 of this function and evaluate it on x4. Okay. And that's the trick. You will just keep doing that. We'll just keep computing the derivative of these functions and evaluating them on the point that it's provided as the input. If we just deploy all these algorithm like iteratively, it's always the same. At the end, we'll be able to compute the partial derivative of y with a hat with respect to x1, which was, remember, that was our first goal. Okay, just notice that this is always the same. It's always just trying. The challenge will be always knowing what the partial derivative is and assessing it at the point of operation. Let's put that into practice now. Yeah, see, I'm just repeating the same. So the steps will always be we need to find the derivative of the functions, evaluate it at the x input, and then multiply it with the backpropagated gradients that in this scheme are the deltas. Okay, so we will be doing is backpropagating the gradients and modifying it by the value of the derivative at the point of operation. Notice, and it's important, that while I was doing all this explanation with y with a hat, in our case, so this will be in general, the chain rule, which maybe you have learned about it. In our case, in which what we want to do is to know how the parameters of our model affect the loss function, because we want to decrease it. We want to minimize the loss function. Okay, so when training neural networks, we will actually compute the derivative over the loss function, not over the predicted value y with a hat. Okay, let's take this concept, this idea, to our exercise, which was computing the gradients for the perceptron. So remember that what we need to do is to know the partial derivative of the operations in the computational graph, and so that when we know the partial derivative, we can assess them in the point of operations. In this computational graph, we have three types of operations. The sigmoid, we have a sigmoid over here. A sum, we have two sums over here,
and products. We have two products over here. So the first thing we need to do is to know what's the value of the derivative of these three functions. So let's compute them. Actually, the first point here is like, so I'll do the propagation. The first one is like, the first point is like the gradient, let's see, of the output with respect to itself. So there will be a 1 that we're going to inject here. And let's start now with the sigmoid. So the sigmoid, here you have a long calculation. I will not follow it now in detail. You can look at it later on your own. But here, what is nice is that there's a closed form for the partial derivative of the sigmoid. And that's actually one of the reasons why we're using the sigmoid, because it's something that we can analytically solve. And this is the form of the partial derivative. Okay. Actually, the sigmoid has its shape. And if you plot the derivative of the sigmoid, you will have this nice shape over here. And as you can see, the derivative is almost 0 at the tails, which is something we already discussed. And the maximum derivative is at the central point, which is almost linear. Okay, so we already have one. Now let's put that into practice. Remember that what we need to do is we need to assess the derivative of the sigmoid, which is this function, at the point of operation. The point of operation is provided by this one. Okay, it's what it's called this dot. So we go at the forward computational graph. It's telling us we are going to look at the partial derivative of the sigmoid and assess it at 1. So here what I do is I implement the sigmoid in F. Here below you have the formulation of the derivative form. And finally, as I put the dot already here, when I assess it, I get this value, 0.19. This 0.19 is what I plot here on red. Okay. Also, maybe I should also mention that actually it's the partial the derivative with respect to x multiplied by the gradient that was coming from this side, which is 1. So actually it is 0.2 per 1, okay, or this 0.2 multiplied by 1. That's why it stays with 0.2. And now we have already the partial derivative at this point. Let's move backward. Now we have the additions. In the additions, we can also compute the partial derivative. So when we have an addition of two values, and we compute the partial derivative for each of the two terms, the partial derivative is 1. Okay, so that's quite easy. When we have an addition, we take the gradient and multiply it by 1. Okay, remember that what you're doing is always take the gradient and multiply it by the value of the derivative at this point. When we have a sum, the derivative, it's always 1, so multiply 0.2 multiplied by 1, 0.2, 0.2 multiplied by 1, 0.2 here, and 0.2 over here. It stays the same. Next operation is the multiplication. Here you have, on the left, the formulation to compute the partial derivative. When you have a product between two variables, and we have a partial derivative with respect to I, the result is B, and the opposite. So this is a bit tricky. Sometimes it poses some confusion. So let's see if we do it well. Here what we have is the gradient. So I'm looking at this node. The gradient is 0.2. That's what comes from here, 0.2. Let's look at the gradient that should result from this branch. Okay, I must take the 0.2 and multiply it. Okay, if I take in this branch, that will be the branch of the -1. What it's telling me, so in this node, it's multiplying, let's say, -1 per 2, -1 per 2. Okay. So if this is a branch of the -1, what the formula is telling me is that I should look at the input that comes from the other branch, and that's a partial derivative. So that would be the 2 will be the result of this formula. And remember that always what we need to do is multiply the partial derivative by the gradient. So I'm having the 2 multiplied by the 0.2. And this is why I have a gradient of 0.4. And if we do the opposite, it's going to work as well. You have the 0.2 and multiply by the -1. This is the gradient that goes through this other branch. Okay? So you can later, if you want, take a look at the rest of branches, but I'm pretty confident that everything is well computed. So what's the interest of this result? So we are done now. We just already reached the input, and we managed to compute what we wanted. Now we want, like, what's the partial derivative of the output with respect with W1, W2, and B. These are the parameters of the model. And remember that this is what we want, because based on this partial derivative, now we'll be able to update this, the values of these weights or this bias in an iterative way. And we can adjust its estimation. And iteratively, hopefully, by adjusting it and re-estimating, decrease the total loss if we do it well. Okay, so these are the parameters that we learn for our models. Notice though that we could also, even it seems useless at this point, we could also compute the partial derivative with respect to our input data, with respect to x1 and x2. We already have them, these values over here. At this point, for today, they are totally useless. But you will see that in some cases, when you try to understand what's going on in a neural network, this might be useful. But for today, it's something we can compute, but we are not interested. I'm leaving you here a couple more of, let's say, gradient weights for operations which are common for the max. If you have at some point some max operation in your computational graph, what you need to do is to route the gradient only to the higher input branch. Okay, so you just discard, don't propagate gradient on the lower branch. So in this case, if the input is 2 and 1, and you have a max operator here, of course the output is 2, and if you have a gradient, say 0.2, that goes through this node in the computational graph, you will just propagate it into this direction, and it sets to 0 on this other direction. In the other hand, if you have a split branch that somehow your data was split, so it's kind of just was spread in 2 branches. If you build networks that have this kind of topology, what you need to do is to just add the gradients. So the gradients that come from this direction and this other correction, just add them, and they will go through. So these are not in the perceptron, but it might be useful in the future. Another important gradient that actually earlier I mentioned that it's interesting, it's the ReLU. So for the ReLU, remember it was one of these rectified linear unit that it's often used, especially in deep neural networks, as an activation function. Most of the neural networks, they're using this activation function. And notice because it has 2 advantages. So first, in the forward pass, it's quite easy to compute the result, because if the input is negative, the output, the input is negative, the output is 0. If the input is positive, you just copy, let's say, the input data to the next layer. But if you're doing backpropagation, so in the backward pass, what you will have is that if your gradient is positive, you just multiply it by 1, so just let it go. But if the gradient is negative, you just kill it. You just delete the negative gradient. So actually, the step function is the derivative of the ReLU, and this super quick, fast to compute, and it has very good optimization properties. And that's why it has been a very important key player in deep neural networks. So if you want to learn more about backpropagation and partial derivative, I suggest that first you watch this lecture from MIT, And later, there's this more advanced lecture by Joshua Benjamin talk about backpropagation. And also, like even here, you have like some more readings that present this topic in more detail, and also like a more philosophical question. Always as useful as usual. If you want to click on them, you can read all the whole advanced discussions. Then I'll just leave you this problem for you to think about, and we'll discuss the solution next week. It's nothing that it's going to be graded, but I suggest that you solve it. If you have questions, I'll put it in as an assignment on the classroom, but if you have questions, just feel free to ask me. But basically, it's just an exercise quite similar to the one that we just completed on the perceptron to compute the backpropagation problem. So this will be the end of this session. If you have any question, please let me know.